this contact probably is still open, isn't it?
Yes.
Yes.
So we'll probably have to show that graphic where that contact is still physically open because we are down, we are in the up position, and that limit switch 1, the limit switch up, is still open.
Right.
And we'll get that changed in the textbook. All right, let's now press the down button, energize the down coil because limit switch 2 is closed. And then press the down button, close the down contact 1, open up the closed contact D2, release the button. I'm able to maintain voltage to the down contact, so the motor is now going in the direction to go down. And once it gets to the end of travel, it has a limit switch that opens it, and now the door is down. I'll have to take a look at my limit switch at my house because I have a garage door that goes up and down. I have to take a look at that. Good stuff. All right, any comments on this one?
Well, the one thing that you may end up throwing into this is the photo eyes down at the base of the garage
So
door.
it might not be a physical limit switch. It might be, it would be a switch that's going to be
Well, I'm talking about
optical.
the emergency
In
to
addition.
where
In
the little
addition.
kids go through and they're one of those, that'll
safety.
override everything, the safety version
Hold
on the eyes.
All right, I agree with that. Okay, so now, if I want to add, what's it, optical? I mean, what is that? It's
Those
an
would
infrared?
be optical, yeah.
Okay, so there's a beam.
Mm-hmm.
So if I hit the beam, that contact that contact would be closed, right? What causes that to open? What is that doing? Is that operating another coil?
Yeah, a little
You have a
relay.
2-pole switch, so it would do just like,
It would override everything
So
that you have.
right along here, I'd have another set. I'd have another set of contacts
Yeah.
with another coil. That when I energize that coil, I would open up the circuit coming to the control circuit and turn it off.
Actually, you reverse it because the photo
They go
eye
back
is
up.
only in the circuit when the garage door is coming down, and if something breaks the photo circuit, then the garage door immediately reverses.
Oh, you're right. We're not going to stop it. We want it to go back up. All right, help me out here. Down. When I push the down button, I energize this. I would then close a set of contacts that would be to the photo eye to activate that circuit, right? Because it only applies when the garage door is going down. Am I right about that?
Well, this is a good example of where you bring Dan in with his PLC. What's happened is in the old days, labor was expensive or labor was cheap and products were expensive. But now in today's age, labor's expensive and electronics has gotten cheaper. So a lot of these garage door openers don't have these limit switches per se anymore. They're all on electronic boards.
Okay.
In-
Yeah, we're not doing
Yeah.
this mechanical stuff anymore. It's all done with a processor.
Right.
And so it's using the electronic image. The concept is the same.
Exactly.
But except it's handling it with electronics. It noticed the infrared. It noticed a change in that signal. It knew it was going down, and that's what the programmable
Right.
controllers got it.
And this is where it's beneficial to go to the manufacturer's diagrams that they have, instead of just throwing them away like a typical electrician
Yeah.
does.
I definitely got
falls.
better reading instructions
Yeah.
as I got older. There's no question there.
you could
All right.
add the, like you were saying, to make it go up, you'd have to use a 2-pole switch, and it would be just the same as your push button interlocks. So you would open one, or your limit switch
Yeah.
interlocks, where you open one and close the other
Right.
to make it go up.
So mechanically, we can get the parts to make it as it's going down. If you see the infrared, then activate something, and then have it go back up. In other words, it's just what Eric is saying. It's a lot of material here, a lot of labor, a lot of work to get something that the garage or opener guys have gotten down to electronics. All right, let's go on. Make a diagram. It can be helpful for the installer to make his or her own riser diagram to help lay out the job. Well, here's an example that if you were going to be using the limit switch down, the limit switch up, and you start push button, you kind of like hand draw this thing out and get your wiring and say, okay, now I know what I'm running and when I'm running, and that's what I did when I pull wire. I just knew what I was doing in advance, and you just pull it in there, and then you make your terminations, and then you take one stage at a time. All right, we're done with unit 13. We're going to unit 14, and maybe these unit numbers are not exactly the same because in case we decide to move something after this recording, and that's a possibility. So if I set a unit number, and well, that's not the same in the book, just not that big of a deal. Reversing single-phase motors. The most common type of motors used for single-phase reversing are capacitive start motors and split-phase motors. Both types have a start winding and a run winding. Okay. Are they actually numbered T1, 5, 4, and 8? Is that they're there?
Very commonly, there's some variations, but that's kind of a standard.
But if they weren't this number, would it be marked somewhere? Is that on the nameplate?
Nameplate, yes.
We'll tell you what the start winding is going to be, the run winding is going to be, and what the start winding is going to be. Okay, so, all right, not more to talk about that right now. Okay, let's see how this works out. Now, Steve, you seem to be familiar with this. Are they marked as a run winding and a start winding? Is that how they're shown on it?
Typically what you'll find is on the nameplate, it'll just show you the connections and say that, now this is wired for the low voltage, so it'll say for 120, connect T1 and T5 to line 1, T4 and T8 to line 2, and then it'll say to reverse, interchange leads 5 and 8. So that's how you know which one the start winding is by that nomenclature.
Okay.
It tells you which ones to reverse, which are your start leads.
Gotcha. So it'll say take T1 and T5, tie them together, put it on a wire nut, and get to line 1. Take T4, T8, tie them together, that's going to get line 2. If you do that physically, let's just say physically we do this, then this motor is going to have, let's say, a clockwise rotation, a positive rotation. Everybody with me there?
Okay.
And then here's the notes that you're saying. Forward, that's what you do. Then the instruction would say, well, if you take T5 and connect it to T4, and I'm going to look at the windings, how this connects in a while, to line 1, and T1 and T8 to line 2, 4 and 5, 4 and 5, 1 and 8, 1 and 8. That's going to be the reverse. Now, I want to go back and look at this electrically. This has line 1, so Mike, put a line 1 here and a line 2 here in the future. And then put a line 1 here and a line 2 here so I can see that that winding is connected in parallel to each other. Is that right?
Yes.
Aren't they?
Yes.
So helps me out. So that means each winding right now would be, if this is 220, then that'd be, 230, then that's 230 and that's 230. You guys agree with me?
Right.
Yes.
Okay. Now, if this is line 1, right? And this is line 2.
They're still in parallel, just different polarity.
I got to follow this. This is line 1 that comes over here, but this is line 2. But this is line 1. Oh, no, this is line 2.
Yeah, we swapped the run leads in this drawing, which will work equally as well. You just need to swap the relative polarity of the start with the run.
1 second. I'm confusing me here. So this would be line 2 up here, right?
Right. It was line 1 before.
And this is line 1 here now.
Yes.
And this is still line 1 and line 2.
Yeah, so
Right.
we didn't change the start, but we changed the run. So all you have to do is change their relative polarity. It really doesn't matter which one you switch.
You just change one of these.
Right,
Right.
It's going to cause the motor then to run in the reverse direction.
right. Usually on the nameplate, the ones that tell you to switch are the start windings, so you know which one it is. We've just done it the opposite way here, but that's fine. It works as well.
Oh, well, okay, well then maybe, then I guess let's just change this in the book then, right? Let's just call, you say it's usually down the start windings?
Usually it's done with the start winding on the nameplate.
All right, well then we'll
In
just,
reality, you can switch either one of them.
all right, we'll just change these all to start then in the textbook. And DVD guys, you know why we changed them. All right? And so that'll be your start winding that we're changing. And would be with changes also to make sure that all this is identical. Okay, well, why not? Let's just make it the way it is. All right, we got that. We changed that one also. The drum switch. So the way the drum switch is working, one, it's an opposition. When I go in one direction, I'm taking line 1 to the start winding to one section, and then I'm taking line 2 to the, I'm connecting them in parallel, right? And when they're always in parallel. I'm just connecting line 1, line 2 on each of the windings. And then when I take the drum switch and I move in the other direction, I'm still maintaining line 1 and line 2 on the run winding. I'm just changing the polarity of the start winding through the drum switch.
Yes.
And then bingo goes back. And what I would be changing is, and that's where you take your drum switch. Now, would a drum switch would have a truth table on it, wouldn't it?
Right.
It would tell me that in this state right here, you have no contacts closed. But if you go in this direction here, then this is going to go to here, and this is going to go to here, and this is going to go to here, and it's going to go to there. But if you go over here, well, then those two and those two are the same, but now we reversed 2 of the leads out of the 4, and it causes it to go in reverse. I wish I had a drum switch in there, and we'll add a drum switch in the textbook. So Mike will pick that up and add a drum switch so you can kind of see how it does switch.
Now this is a single voltage motor. We might just want to make the point that if you did have a dual voltage,
Hold on. I'm glad you brought up voltages. Would this matter? Can you only reverse a single-phase motor if it's phase-to-phase? Can you do this to a
Doesn't matter.
120-volt motor?
Yes.
Washing machine motor.
Yes.
Okay.
The difference being if it's a dual voltage motor, then you've got 2 run windings in there that you're going to hook up either in series or parallel.
Hold on. Slow this down here. All right. So it's a 120 or 240-volt motor. It won't, I mean, if it was just a motor, not a dual voltage motor, then it'll work the same way as what we
Just the
talked
same.
about.
Exactly.
If I have a dual voltage motor, which would be, let's say, a 120, 240, tell me what's it going to do there.
Then the most common motor, you have just one start winding and it only parallels one of the run windings. They make variations, but that's the most common. So you only want 120 volts on your start winding, but your run winding, each segment has 120. And you can put either those either in series or in parallel, depending on your supply.
Now, how would I know if I got that kind of motor? What would be the switching that would be required?
Well, the leads on it, again, would have both the high voltage and the low voltage hookups on the nameplate.
Okay.
Because you're going to have to series or parallel that.
Okay, you're
that
going to hook
start
them up.
winding, or the run winding.
You're going to hook them up so that they work on the lower voltage. But once you do that, then you need to switch the windings, one of the windings, the polarity of one of the windings.
Mike, I believe that on the single-phase motor, that's why you have T leads T1 through T8.
Yeah.
Because on a dual voltage motor,
Right.
your run will be T1, T2, T3, T4.
Exactly, which
Yeah.
where you're picking up.
Right.
So you hook it
Fill it
up
in
first
there.
of all, so it runs on the low voltage, and then you start making your connections to get the reversing inside there. Excellent, excellent, excellent. I can do this. Well, we're now moving into Chapter 4. Some applications, such as assembly lines, use multiple motors which must be started or stopped in a certain sequence. And this chapter is going to be talking about that. Let's go to probably Unit 15. Maybe it's 14. I'm not sure how the number is going to be. This unit explains how the control circuits of magnetic motor starters can be interconnected so that one must be started before the second one is energized. This type of control is often required for auxiliary equipment such as high-pressure lubricating and hydraulic pumps that must be operated before the machine itself can operate. Dan, can you give me some examples? Do you guys have processes that you have to start this and then it goes down the line?
We have many processes from conveyors to like what you talked about, pressure lubricating systems and hydraulic pumps that can be on before machines can be operated.
And you guys have all kinds of sensors to make sure that things are in a certain condition before you even can start the first one, and you're checking it all out. That's why you're using programmable logic controllers. PLCs.
Yeah, there's a lot of times that you have a lot of complex circuits where you would have a temperature switch or a motion switch to prove that something's running, or a pressure switch or a flow switch.
So you not only want to start this one, but you want to prove that this one is actually functioning before we start adding on the next item, etc.
Yeah, for safety.
You're not dropping the box until you know the conveyor is moving.
Correct.
You want to know that it's moving, not that the contact is closed for it to move,
Yes.
and at a certain speed or whatever other characteristics. And how about Dow Chemical?
Oh, all the time. If we have a large machine that requires lubrication, for example, we'll need to make sure that the oil pumps come on first, get the oil up to pressure, and only then will we start the machine.
Okay, let's take a look at some graphics here. All right, let's see how the sequence goes here. Press the start button, energize the M coil, close the M1 contacts, interlock the M coil, close the main contacts and motor. Motor 1 has started. Once motor 1 has started, instantly at the same time, the M1 contact closed, the M1 contact in... Oh, I think this is,
That's another stop-start circuit for motor
oh, that's
two.
a separate one. Okay. Okay, so now this contact closed, but that motor hasn't started
Correct.
because this coil had to be energized to close the contact in a separate circuit for a separate coil. That now that this is closed, I press the start button. Now I can start the next piece of equipment or energize the next M2 coil, which closes the M2 contact, which now interlocks the M2 coil. Now the second stage can continue to operate.
Right, Mike, a lot of times that M1 contact that's in the lower one, that's 4 and 5 there, many times that's called a permissive contact because it permits the M2 to energize.
I love it. Excellent, excellent. Well, let's take a look at this right here. Here's the sequence of it. Let's go. You press the start button. Oh, here. Now I got voltage going to one side of the coil. Done. Come over here. Goes to the stop button. I get voltage start button. I press the start button. I get voltage over to the M coil. Energize the M coil. I close. Oh yeah, close the 2 and 3 point, which continues the voltage, that's the interlocking contact. It's the auxiliary contact that's interlocking, right? It latches that coil. Then I use and you said this, Dennis, that you can add auxiliary contacts, normally open or normally close or whatever you want to. So we added a set of contacts, and then we came over from this second motor, and we go through the auxiliary contact on the first motor, that if the first motor is running and this contact is closed, then we're going to get voltage to the start-stop button of the second motor. And if, permissively, we get voltage here, press the start button, get me voltage to the M2, because M2 already has the voltage on the other side from the L2, energize the M2 coil, close the M2 auxiliary contact, which then interlocks the M2 coil. Good. I have no problem with that. Makes sense. Yeah, okay, both motors are off. That was our state. And motor 1 is running. So now we have voltage going over to the control circuit number 2. And that allows me to press the start button, which energizes motor number 2. Controls for sequencing multiple motors. Here's an example where we have, well, like you said, Eric, motor 1 is a loop pump. Motor 2 is to drive it. We have a time delay relay. We have a loop pump pressure switch. And then we have a start-stop button. Oh, and then we have a motor 3. All right, let's see what the process is going to work out. What else we got here? All right. We have a ladder diagram. This is clearly showing what the ladder diagram, how it works out. We got a stop, we got a start, we got motor 1 coil, we have motor 2 coil. Which is a timing relay? A timing
Yes.
relay. You have to tell me more about that in a second. Then we have motor 3. All right. If I press the start button, we have voltage on the line 2 is taken care of. Here's a time. Oh, here's a time relay contact. Here's a lube oil pressure switch. All right, let's press the start button. I press the start button, energize this coil, close the M1 contact that interlocks the motor. So the motor's now running. I now close M1, permissive contact M1, which now permits the motor 2, which was the, the lube oil comes on. Motor. I got permissively until the lube oil pressure indicates that there's sufficient pressure. Once it gets to the point of sufficient pressure, it closes this contact.
Right.
That immediately starts the main press. Also, it starts the time delay relay, which now motor 2, okay, I got the oil going, I got the main press now running, and then there's some kind of time delay, and Dennis, you showed us yesterday, or Steve, you did all the different time delay configurations and however you wanted to do. Then, let's say 5 seconds later, this closes. Now the third motor is energized. And so that's your start. Energize the coil. Here's your lube closing. Energize the second one. Here's the time delay closing, energize, and Mike did a great job of having all these graphics right in order like that we can see that. Eric, you got a comment there?
Yes, this is a small solid-state timer that you can see the contacts here, and it's adjustable with these switches.
So tell me more about that. What does that mean?
Well, and so this might be where you might introduce that time delay for that time delay relay. You could either use a time delay relay like this, the white
Yeah.
button, and adjust the time delay here, or you could use a standard relay with a solid-state timer.
And how do you adjust that solid state timer?
There are switches here, which
Little dip switches.
the little dip
so the
switches.
instructions say that this and this and this gives you this and this time. and-
Correct.
All right. Now, is one called analog? Is the one with the one that you can turn analog? That one right there, or is not really?
Well, that's a good question. They could. This is probably analog right here because it has a potentiometer on the top. This one could also be analog, but you don't know. Could be digital. Could be
Okay,
analog.
so you can't really tell.
Can't really tell.
I just try to use that word analog whenever I can, so I can look important. All right, and here's the wiring diagram for the different motors, and I'm not going to get into that. And I'd have to sit down quietly, draw this out, put this together, do my hand-drawn graphic, kind of something like this here, and then put that together. All right, we're done with Unit 15. Moving to a master stop function. Well, this is going to be a short unit, like some of the other units are. Sometimes what you want to do is you want to make sure that a whole process stops with just one button, an emergency or a master stop button. Well, if you want everything to come off, then you want to make sure. Here's an example where you'd want to have a separate circuit for your control circuits, right? Not tap off of each motor branch circuit. You want to make sure you have 20 amp breaker at the panel, and you come over, and now you can supply all the different controls that you want to be able to turn off, and put a master stop button right there, and you just run over there with maybe a mushroom head, boom. Probably should show this with all these things energized. If all these things are energized, and maybe the next slide or two after that, this is off. You press start, you get them all energized, and all you got to do is press one stop button, which will turn them off. And then Steve has a picture. Does that say emergency
It says
system?
emergency stop on that ring. Can you see the ring around the?
Yeah, turn it down a
Hold
little
it
bit.
down a little.
Well, that's the kind of stop button they put, I guess, in gas stations, right? Emergency stop button.
Fuel cutoff.
Cut it all off. Drop all the dispensers at one time. And that one might be cutting them off at the panel, might be turning off the entire panel. I'm not quite sure how that all works out. Okay, well, now we're moving into an area that we're going to call the annex. Now, this is our first book on motor control. Actually, it's our second book on motor control, and revise it. And we're making some decisions, and so we're adding a section called an annex. And what we're going to do is we're going to add a couple items here. The first thing we'll do is going to talk about a couple of diagrams and schematics and some wiring, just kind of something that's going to be useful. And Mike will be adding a whole bunch of other areas into the annex. Gives us some opportunity. We want to add possibly the National Electric Code Article 430 requirements to this, as well as other items. So I'm going to finish this up on some items that we know we're covering in the annex, and then there'll be some additional bonus items that'll be contained in the annex. All right, let's go on. Motor winding connections. This unit explains, or this section explains, lead designations for different types of three-phase motors. All right, we got dual voltage 9-lead three-phase motors. Let's take a look at this one. Most common would be at 230 for low voltage and 460 for the higher of the two voltages. All right, let's see what we got here. So if we have a dual voltage motor and we're going to connect it to line 1, line 2, and line 3, which ultimately goes to T1, T2, and T3, but you have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 terminals. And the nameplate would indicate for line 1, connect T1 and T7. Let's see, line 1, T1 and T7, connect these two together. Line 2 is T2 and 8. That's 2 and 8. And line for low voltage, and line 3 would be 3 and 9. 3 and 9. And then it says tie 4, 5, and 6 together, so I'm going to tie 4, 5, and 6. So here's an example. 1 and 7, 2 and 8, 3 and 9, and tie 4, 5, 6 together. That'd be your lower of the two voltages. High voltage connections, 1, 2, 3, and then tie 4 and 7 together, 5 and 8 together, 6 and 9 together. So T1, T2, T3. Now I know where the T comes from, why it's T1, T2, and T3. Terminals. And then you have 7 and 4, and 8 and 5, and 9 and 6 tied together, and that's how you connect to different voltages. Let's take a look how this, what does this mean? The voltage source would be 230. The nameplate would be 230, 460. But the nominal voltage is 240, 480. So don't allow that to confuse you. So we got a 240 volt source coming into a 230 volt rated motor because of voltage drop. And you have T1 and 7. Okay, 1 and 7 gets connected. As 2 and 8 get connected, and 3 and 9 get connected. That means I'm connecting these windings in parallel to each other, aren't I? So this whole assembly. So these 3 windings right here are going to get connected to 230. These 3 right here are going to end up getting connected to 230 as well. That's for the lower voltages. If I go to 480, that means that this voltage here is operating at kind of like 120, 120, 120, 120, 120, 120. And then when I go to 460, I'm going to connect this 2 windings in series to each other at 460. No, I'm sorry. This is not 120.
240 divided by
Sorry.
the square root of 3.
Yeah, okay, we can't do it that way. It can't work out because you got the configuration different. But this is going to give us 2 windings at the higher voltage, and this gives me 1 winding at the lower voltage. So the windings are both going to get the same potential. And so at the higher voltage at 460, you go T1, 2, 3, T1, T2, T3, tie 4 and 7 together. 4 and 7 get together. 5 and 8 get together. 5 and 8 get together. And 9 and 6 get together. 9 and 6 get together. And that's it. Let's go to delta. Help me out, guys. Why do I have a Y configured motor, and why do I have a delta configured motor if we still have 230, 480? Anybody know the differences and why?
It's not real important whether you have the Y or it's just the construction characteristics of the motor, unless you use the Y start delta run for a reduced voltage start.
Okay, so if you're an electrician, it doesn't really matter because the nameplate on this motor is going to show you a different set of connection leads. Why it's a Y, obviously it has to do with design, and there's issues, and there's things beyond the scope of this control class that we have to worry about, but we're trying to help somebody know how to hook up the motor. You just, in other words, you can't go to this wiring configuration and think that applies to all motors. You got to go to the nameplate and hook it up according to the nameplate and not worry about what's going on internally. And then if you go to this motor here, it's a different kind of motor, so therefore the leads will be connected differently because this low voltage is 1, 6, and 7, and 2, 4, and 8, and 3, 5, and 9, and nothing else here. But then the higher voltage is still T1, 2, 3, but then it's 4, 7, 5, 8, 6, 9. The other one was 4, 7, 5, 6, 8, 9.
The high voltage is the same, but the low voltage is
the
different.
same, yeah.
Yeah. So the low voltage are different. And it doesn't really matter. Eric?
Yeah, I want to bring up something real practical about a dual voltage motor. You mentioned nameplate earlier, and it'd be good to get an example because in a 230 460 volt motor, you'll see on the nameplate on voltage 230/460.
Right.
But in amperage, you'll see, for example, 4/2.
Right.
And that's real important because you pick your overloads based on nameplate amperage. And I've seen where I've watched a contractor put in an overload on a starter element, and I said, well, wait a minute, that starter, that overload looks a little bit high. So I went out to the field, read the nameplate, and he had connected the motor to 480, but was using the 240 amperage to size his overload.
Not understanding when you have a slash voltage and you have a slash amperage, that the first voltage and the first amperage are connected together.
Right.
And if we had a nameplate, and the second voltage, which would be the higher voltage, would it be connected to the second amperage, which would obviously be a lower amperage.
Right.
Good point. any, oh, by the way, I remember hooking up a three-phase motor once with all these leads, and again, I was like, what the heck is this about? I didn't know. All you had to do was go to a book somewhere, and now today we got the internet with my little iPhone, and just boom, 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 boom. I'm sure I can go to iPhone and, three-phase motor connections and pop it up, and there's the leads, and that'd have been easy. We didn't have the source then. I didn't have the education when I was first working, but I think I remember one time a motor that the leads were cut. There was nothing put on the leads. So what do you do if you get to a motor and it doesn't have any of the numbers? Do you just tell them, you better get another motor, or you better get somebody to identify? What do you do? Because how would you know if it was a Y connection or a delta connection? Any such a...
An ohmmeter can help you get that far to figure out if it's a Y or a delta. Because
Okay.
with the delta, you're going to have 3 sets of 3 leads. And with the Y, your continuity is going to be 1 set of 3 and then 3 sets of 2.
You're going to have...
Just your
Here,
continuity.
you got a set right here.
Yeah, you can
find.
figure out those sets
You
right
can
away.
find these sets, and you can find these sets, and then you'd find out, hey, these 3 are all common.
And there is a method that you can use, and I don't recall the whole method, but again, you can go on the internet and find it probably, where you can tie them together and put a...
So you can maybe tie these together, or tie it to something, and
Well,
you'd find out...
It's something like you tie 2 of the 3, like 7 and 8 together to one line, and then you just bump the lead 9, and then you put an ammeter on each of the other, like the 1 and 4, to find their polarities.
All right, we
I
won't go
don't-
any further
No,
other than
but
to
there is a
say
method. There is a
a method. You need to go on the internet. Somebody's already done the research that will tell
Yeah.
you step number 1, connect this, and then slowly you can make the lead
Yeah.
connections. Anything else on motors? Windings?
Well, you mentioned about not marking some of the wires. Whenever you have a motor rewound, they will probably take the dual voltage away and just bring out 1 set of leads, and they don't always mark them 1, 2, and 3.
So then you won't know rotation.
You won't know rotation, but you will know the voltage because you will have told them what voltage you've been running it on.
Gotcha.
And they do that just to save cost.
Okay, is there any reason to have a dual voltage motor? I mean, is it cheaper to buy, not a dual, or do motors just come dual voltage because it's just easier that way? Or what's the deal here?
It's cheaper for the manufacturer because they don't have to stock 2 different motors, all the iron and all the copper and everything that goes into them.
Okay.
Or if you're building a piece of equipment and you don't know what kind of distribution system it's going to go into, it gives you options.
Makes sense. Makes sense. All right. The last thing that we're going to cover, and I don't have the graphic really to do a good job on this, and I apologize. It's something that we thought about. Let's add to the book, and there'll be a little bit more graphics in the textbook with maybe a little bit more text to explain that. Is going to be a simple air conditioner, little thermostat. It's going to be single stage. It's not going to be a 2-stage. Here's your compressor, and there's going to be a set of relays in here. Oh, no, there's going to be a relay that's going to be operated by a 24-volt control, and I guess that'd be AC control. And then we have a thermostat. Then the air handler, in this example here, that this would be, let's say, a heat pump only, without any supplemental heating. This is just good on or it's off, so there's just one relay with a set of contacts. And then we have the heating element, which would also have a relay that will turn on the heating element. So that's one relay with 2 wires. This is the compressor with 2 wires. Then I have the blower. That'd be another relay. That's 2 wires. Then we'd show the transformer. Well, that's going to be primary 2 wires, secondary 2 wires. So I have 2 wires off the transformer, 2 wires from the heating relay, 2 wires from the fan relay, and 2 wires from the compressor relay. And somehow I got to get 2, 4, 6, 8. I think there's 8 wires. Somehow I got to get them together to the thermostat. So let's just take our time. Well, the practice, well, no, not the practice. I guess the standard is your thermostat is going to have a yellow terminal, and that'll be identified for the yellow wire. That's usually what W means, the Y. The thermostat will have a W terminal. That would be for the white wire. It will have a G terminal for the green wire if you use color coding. If you actually use these colors. And it will have a R terminal for the red wire. And it will not have a terminal B at all for the common. It's just going to have yellow, white, green, and red. And this is a single-stage, simple thermostat, not 2-stage. The practice is, let's just assume that we're pulling we're running a raceway for convenient purposes, and we're pulling our conductors, and we are going to color code the conductors. Are you with me? So we have control of color. If that's the case, yellow is for cool. That's the compressor. I would run a yellow wire over to one side of the relay, and the other side of the relay, I will then take a common conductor, and I'm going to use the color blue. So the common conductor comes back. If this was the wiring configuration, the blue wire comes over to the thermostat, and since that's common to the transformer, the blue wire will travel over through this cable and go back over to the blue terminal that's going to go to the common of the transformer. If I can take 24 volts to the relay of the compressor, it closes those contacts, compressor kicks on. Let's talk about the fan. The fan has a common that also goes over to the transformer. And the fan is going to be controlled by the thermostat, and the fan is the green colored conductor. So I'm going to take a green wire from the thermostat to the fan relay. I'm taking a yellow wire from the thermostat to the compressor relay. Then I have the heater, and heat is the white terminal or the white wire. Then from the thermostat, I'm going to take a white wire to the heating relay, and the heating relay has a blue wire going over to the common of the transformer. So what do we have? Oh, then I have a yellow for cool. I have green at the thermostat for fan. I have white at the thermostat for heat. I have the common conductors not making a termination at the thermostat, but all common conductors go over to the transformer, common terminal. Then I need to have power to the thermostat. I leave the transformer secondary, and I run a red wire to supply the thermostat. If you take the red wire, and you take the red wire, which is your power, and you touch the green wire, the blower should blow. You'll hear it turn on. If you take the red wire and you touch the compressor, of course, assuming power's on there, you'll hear the compressor kick in. You take the red wire and you touch the white terminal of the thermostat, then you're going to be smelling the heater elements heating up without the ability to cool them down because we're not moving any fan. So the way a thermostat works out is that when it goes to heat, it closes two sets of contacts. It closes the contacts for the W, for the heat, but it simultaneously closes the green contact in the thermostat so that the fan is going and the heating is going at the same time. When we go to the compressor mode, where the thermostat says cool, gets voltage to the relay for the compressor. At the same time, it energizes the green wire, closing the fan so that the fan works at the same time the compressor works. So the fan goes with the compressor, fan goes with the heat, so it's going to run in both times. And that's the simple basics of a basic thermostat. But we're going to add two-stage and maybe some other thermostats to the textbook. Any comments at all on this, guys? Steve?
Yeah, like you say, that's the simple of it. There's also some things in there they might want to need to be aware of, like time delay relays and various things that stage things off and on so that the fan will come on before the heating elements or before the gas pilot or the gas. So there's some timing that takes place in there too, but it doesn't affect the thermostat.
All that timing is all done by the equipment.
Yeah, in the unit.
So now I know I have a thermostat. It has multiple stages, and it has supplementary heat, and it has a heat pump, and it has resistant heating. And when I looked at my wires, I'm like, I have no clue.
Yeah.
And guess what? You don't have. I think it's like there's like a W1 and a W2, and then there's a yellow, a Y1. In other words, in that particular application, if you get more than this basic thermostat, you need to get the thermostat. You need to understand the wiring diagram as, okay, what wires am I supposed to bring? Because you now have multiple staging. You have supplementary heat that kicks in when it gets below a certain temperature that the heat pump is no longer being efficient. Then all of a sudden it goes on to resistant heating. There might be supplementary heating in the heat pump itself, and then you have additional heating in the actual air handler. So it can get pretty complicated. What I didn't know, I told you the story, my first experience. When we started this thing, I got fired because I couldn't hook up this thermostat. I didn't know and we didn't have the technology then we have today. All I needed was the instructions.
Yeah.
I didn't have to know off the top of my head how to hook this up. I needed to have the instructions to that equipment for that thermostat. What are we trying to achieve? If I had the knowledge of that, but like you said, Steve, if you just go somewhere and there's no thermostat there and you got a bunch of wires sticking out for a thermostat and you don't know that there's controls and delays and how this all work out, you can't just be taking a thermostat now trying to make the things work. You're going to have to get with the manufacturer. You're going to have to understand the process and what needs to be achieved and make sure that you have the right thermostat and then go through it and you're going to be fine. So hopefully, don't feel like you're supposed to know this. You're supposed to know that you need to get the information, get a quiet spot, sit down and look at that without people breathing on your neck like, well, you're going to get that done? What's going on here? I thought you had it done by now. You know, that whole thing works out.
And then it's all series or parallel relationships.
Yep. I tell you what, yes.
Well, also with thermostat, I can't emphasize enough, keep the instructions and look through the instructions because there are other things on thermostats. For example, sometimes you open up, there's jumpers on a control board. And if you cut the jumpers, then you cut them to provide different options like a regulation band and this, or if it's Celsius or Fahrenheit, for example. And so really look at those instructions.
Okay. Well, it's about the best we could do right now. And I'm sure that we can do a better job in the future and we'll continue to improve. I hope we're able to achieve what our goals were, and that was to take you from knowing nothing about controls, giving you the foundation of some basics, the terms and how these things can be approached and how you can solve some of the problems and give you the confidence to know that you don't have to know everything. But also, as you gain knowledge, you become the go-to person, and Steve keeps saying that, and that's when you become more valuable for yourself, for your family, for the industry, for the employer, if you're not the employer itself. So we're always striving to be better and better and better. Please visit our website. Our website is MikeHolt.com, and, you know, there's so much free tools. There's newsletters that go out there. If you have a question, like how does this work? I mean, you had a control question, you can just go to our MikeHolt.com, go to the forum link, and post a question. And trust me, you know, you're going to get your answer. How many of you guys here on the forum get my newsletter? So all you guys get the
All of
newsletter.
us.
Okay. And so the key is those people that really want to stay connected. I send out a newsletter 3 or 4 times a week about a lot of different things, and you can decide whether you want to read it or not. If it's not important to you, you delete it, and you can choose the topics you want to receive. You have questions you can post in there. There's free software. Please, please, please go to MikeHolt.com. Take a look at all the free links and all the free information. Then if you find out that you need a product, you want to educate yourself, you want to go to the next level, you know, we'd love to be able to help you. You know, there's something you can order online, or you can contact our office. Let's get a closing with these guys here. Let's see what these guys have to say that maybe they can kind of leave you something, rah, and then I'll leave you with something. Steve, we'll start with you as we always do. One second. You know what? Before we do that, I don't want to take a time and just, you know, thank these guys. I mean, you know, I'm just a facilitator in this particular course, but even if I was the expert, these guys are experts on top of what we do. And as a team, we work really, really carefully. We work together to give you some insight, little tiny things of information. I mean, I've been in the trade now since 1970, so that's what, 38 years. Steve, how long have you been in the trade?
74. So
74,
34
80,
year.
34 years? Eric?
I guess about 32.
32? Dan, you're probably a young pup here. How long have you been?
Well, I started out as a millwright, but
No,
I've
we
been
don't count that.
Christian since in '88. So
Okay, 88 now, so 20 years?
20 years.
29.
29 years? So you got, and Mike Coberth, how many years?
74?
74, so you're about 34 years like Steve.
Yep.
You know?
About the same
So
exact.
we're talking 100-something years of experience in all different aspects coming together, bringing the combined knowledge to give you the tools you need. And so I want to thank these guys because they've done a great job. And I tell you what, I feel a lot more confident in controls. So I think that's great. Hey, Steve, tell these guys something.
Well, I just like to encourage the guys, you know, that even if you just got a couple years experience or just a beginner, you know, to feed your thirst for knowledge. You know, the more that you learn, the more that you know, the more you're going to be the go-to guy, and the more satisfied you're going to be with your work. If you can understand what you're doing, it makes it much more enjoyable. And Mike has got just a wealth of products for the electrician, not only on controls, but on electrical code and theory and all those things. So anytime you can learn, it's going to help you to better yourself.
All right. And Eric, my engineer.
I'm going to go back to the statement that I thought of several years ago. It's the power of knowledge versus the pain of learning. And all learning is painful and uncomfortable. But if you can submit yourself to it and commit yourself to it, the knowledge that you get from that gives you power to do things and to make your life easier. Ultimately, all of this stuff makes your life easier.
Dan, this is a new experience for you because these guys have been doing this for almost 6-8 years for me in this video team, and this is your first time that you've had opportunity. And I want to thank you personally because I think you've done a great job, and we're really, really pleased that you're here. And so next time we do the motor control course and maybe other courses, we'll make sure you'll be part of the team. So anything you can convey to the student watching this?
Well, thank you, Mike. I appreciate that. You know, I'll go back to saying that the basic 3-wire start-stop circuit is the most important circuit you'll learn. I'm glad that we've helped Mike to appreciate it as much as he does now.
That's true. I love 3-wire circuits.
But that's the basic building block that you'll build on, and it's used over and over when you get into the more, complicated circuits, and you get into the PLCs, you get into if-then-else statements, you get into wonderware, or, operator interface controls. The start-stop is a basic building block of everything that you'll build from.
Well, thank you. Appreciate that. That's great. Dennis?
Just go back through the videos, go back through the book, pick up equipment like this, and take a meter and just sit there and take some time and troubleshoot it and get a good feel of it. And you got to stick with it. You got to review it, and you'll get a better handle on it. It'll come.
All right. Well, I'll give just a final little thing. I appreciate it. Appreciate you taking the time, really to watch this DVD. And if you get a chance to completely read that book and answer those questions, Mike Horwath, he's working as a team here. We're doing a good job. And Mike, you did a great job. Everybody loves your graphics and appreciate everything you do for the industry. And God bless. Talk to you guys later. Bye-bye. Let's take a look at Article 430. Motor circuit.